Hello everyone. So in this experiment, we're going to use the ball drop apparatus to measure the acceleration due to gravity. So basically we're going to measure the acceleration of any object. In this case, we're going to look at this marble. When it's in the vicinity of the Earth's surface, we're assuming no air resistance. If we release it, right, it accelerates downward with some value, and that's what we want to find. Typically we call that g. And theoretically, it's around 9.8 meters per second squared, or 980 centimeters per second squared, if we're using CGS units. Okay. So how are we going to do that using the ball drop apparatus? Well, the idea is really simple, actually. We have two photo gates. There's a ball dropper up here, so the ball will be in a dropper. I'm going to release it. It'll pass through the first photo gate, the second photo gate, and then land in the catcher. Okay? And we're actually getting three pieces of information. We're getting the time it takes the ball to pass through the first photo gate. We're getting the time it takes the ball to pass through the second photo gate. And we're also getting the time it takes the ball to go from the first to the second photo gate. In your lab handout, we call this delta TA is the time it takes the ball to pass through the first photo gate. Delta TB is the time it takes the ball to pass just through the second photo gate. And then delta T12 is the time it takes the ball to go from the first to the second photo gate. Okay. Why does that give us enough information to calculate the acceleration? Well, if we know the size of the ball, the diameter, right, it's around 1.90 centimeters, and I know the time it takes to pass through that first photo gate, then I can use the diameter, which is like my displacement, delta x, divided by the time it takes to pass through, that's my delta t. And if I divide, so delta x divided by delta t, I get a really good estimate of the velocity at photo gate A. Okay? And we call that VA, the velocity at photo gate A. I can do the same thing at photo gate B. I know the diameter, 1.90. I can divide by the time it takes to pass through. That gives me a really good estimate of the velocity, VB, at that instant, right, the velocity at photo gate B. And then finally, if I know the time it takes to go from the first to the second photo gate, so that delta T12, then I can take the velocity at B minus the velocity at A, so like delta V, divided by that time, right, to go from one photo gate to the other photo gate. So remember, delta V, change in velocity over change in time, gives you the acceleration, right? It gives you the average acceleration, but in this case, we know that the acceleration of the ball is constant. In fact, it should be equal to around g, so around 980. Right? Let me just show you a couple of drops, like how this works. So it starts in the ball dropper. I usually start it around halfway out. It tends to work better. It doesn't always land in here. Hopefully it will this time. So I will release it. Okay, it landed in. And then from the CPO timer, I'm getting, when both lights A and B are on, I'm getting the time it takes to go from the first photo gate to the second photo gate. If I leave just one of the lights on, I'm getting the time it takes the diameter of the ball just to pass through A. And if I leave another light on, say B on, I get the time it takes the ball just to go through B. So with one ball drop, I'm getting three pieces of information, 3 times. And that will allow me to calculate G. Okay? The only other thing that comes up in your lab is at the beginning of this, we need to know the time it takes the ball to fall the first 15 centimeters, because later on, the first photo gate, this is sort of like the general setup, the first photo gate will stay 15 centimeters below the ball dropper, and the second photo gate is going to move. So at first it'll be 10 centimeters below the first, and then 20, 30, 40, 50. So there's 5 different conditions It's the position of the second photo gate relative to the first photo gate. But for the very first part of the experiment, we need to know, because we're leaving this first photo gate A at 15 centimeters below, we need to know the time it takes to go from the ball dropper to that first photo gate. So the way we have it set up, and you guys will see this in your handout, is the first photo gate is going to be right before the ball triggers it. So I have the ball halfway out. You can see like the slit in the photo gate, so I have it just below. And then I would measure this. I'm just going to approximate it right now, but I would measure this so that the distance from the first photo gate to the second photo gate is 15 centimeters, and then do 5 ball drops where I can get that time from the first to the second photo gate, and that will basically be the time for the first 15 centimeters. Okay? You will need that later when we do a graph of the velocity at the second photo gate versus the time it takes to go from the ball dropper to the second photo gate. Okay, so that should give you sort of an idea of how all that data was collected using the ball drop apparatus. Great, thanks.